Yeah, good. Good morning, everyone. Good to be back to ICTS, wonderful place, and I hope I don't need this. Okay. So, in fact, this series of lectures has been requested by the organizers. I cannot be sure that I know where it fits in the program. So I think these lectures will be perhaps quite disjoint from the rest of the program. I did look up some of the abstracts and they all seemed very high. So at least I hope you can follow these lectures, which at least for today, they will presume no knowledge, at least for today. I believe for most of my lectures, I will give mostly very elementary lectures, but I cannot be too sure. All right, so these boards are a bit too big. Okay, so the GGP conjectures are about branching laws. Conjectures are about branching laws. So I think today's lecture, I will mostly talk about branching laws in general and come to the specific of GGP conjectures in the subsequent lectures. So by branching laws, one usually means that given a representation phi of a group G, the question is how does phi decompose when restricted to H? So this is a question which has been studied in many contexts, and it indeed plays quite an important role in trying to understand the representation theory of groups. So to give examples which are relevant for what I will be discussing, the first one is called the Klebsch-Gordon theorem. And this is about tensor product of representations of SL2C. Tensor product of representations of SL2C. And these representations are irreducible representations of SL2C. So we denote pi n to be sim n of C2. And here n is greater than or equal to 0. So one knows that these are the only that every irreducible representation of SL2C is one of these. And the Klebsch-Gordon theorems are statements which tell you how this representation of SL2C decomposes. And the theorem is that this one is pi n plus m dot pi n minus m, assuming n is greater than or equal to m, and in steps of 2. So indeed, this one is basic to many subjects. certainly as a, and, G is SL2C, and this is, so you see in this case, one looks at representations of G cross G restricted to diagonal G. Tensor product is a special case of the restriction problem in which one looks at the restriction to the diagonal. And the other example of great beauty, example 2, is about restriction problem for representations of GLN plus 1C restricted to GLNC. So in this case, one knows, so just like, this example began by saying that the irreducible representations of SL2C are of this form. So somebody proves that, and then this is the next step. So here also, one needs to say, so one knows that irreducible representations of GLN plus 1C are parameterized by an n plus 1 tuple of integers which I will denote by lambda bar, and these integers are in this form. So this is a very classical theorem, perhaps several hundred years old. And what one wants to do is to restrict these. So these representations denoted pi lambda. And what we want to do is to restrict these representations, which are finite dimensional, irreducible, for GLN plus 1C, and we want to restrict it to GLNC, and we want to see how it decomposes. And the theorem is that pi lambda restricted to GLNC is direct sum of pi mu. So these are representations of GLNC, and so therefore mu1 greater than or equal to mu n, and this is mu bar such that lambda 1 greater than or equal to mu1 greater than or equal to lambda 2 greater than or equal to mu n greater than or equal to lambda n plus 1. So the highest weights which appear in the restriction problem from GLN plus 1 to GLN are in this nested sequence. So in a certain sense, the GGP conjectures bear on these examples, and in due course, we may say something more about them. Okay, so what I want to highlight about these examples is some features of these examples, some features of these branching laws. So, I want to kind of bring out some features. some which will play an important role and some which are specific to the situation at hand here, but will not be true in general. So the first feature is that we are dealing with finite dimensional representations. In these examples. The second feature is that all these representations of G restricted to H are completely reducible. So, you know, this is a very important feature of representation theory of finite groups, which you study in all courses about finite groups in characteristic 0. What that means is that the representation restricted to H is a direct sum. And somehow it makes sense to say which representations appear. And the third feature is that there is a multiplicity 1. Each case. And the fourth feature is that any branching law depends on explicit knowledge of representations of G as well as of H. So, you know, most of my lectures will be devoted to P-adic groups, for which almost all these features are lost. So we will not be dealing with, okay, so in these lectures, we will be mostly dealing with P-adic groups, dealing with P-adic groups, such as GLN of QP, or also real groups. Real groups like GLN of R, where number A and number B are just not there. Where A or B is not available. And the C is available interpreted properly. But C is available when interpreted properly. And regarding D, that is somehow where we need to do larger work. For finite dimensional representations that we were discussing in those two examples, it is what is called theory of highest weights due to Cartan and Weil. So D for finite dimensional representations is called highest weight theory due to Cartan and Weil. So there is a rather complete understanding about finite dimensional representations of algebraic groups, a theory which is about 100 years old, and although it is an old theory, I think it is still a model to have in mind. So in the case of real and P-adic groups, we want to more or less try to do something of this kind, that we have a representation of a group like GL and QP. So G equals GL and QP, and H is equal to GL n minus 1 QP, and pi a representation of G, and then we want to understand how does pi restricted to H look like. That is what the GGP conjectures answer. So, you know, an answer to a question of this kind obviously must have as input some knowledge of what pi is. There should be a way to identify representations of a group. And then there must be a way to identify representations of H. So the GGP conjectures depend on a complete understanding of the representation theory of real and P-adic groups. And I mean, complete understanding of representations of real or P-adic group is perhaps a bit of a tall order, but there is a way to parameterize them. And that is what is called the Langlands parameterization. So part of my lecture will necessarily have to go through what is called the Langlands parameterization of representations. But today, to keep it accessible to everyone and to feel that these questions are of interest and that one can perhaps understand some of them, I think I will come back to the Langlands parameterizations in my second or third lecture. There is also quite a detail about what groups G and H one considers. So those details will come up in my next lecture. Basically, we are going to deal with classical groups. And over complex numbers, classical groups are somehow bit easier. But when we are dealing with P-adic groups, even classical groups need some background. So I think my second lecture will be something to give some understanding of classical groups over P-adic fields. For the moment, I think in today's lecture, I want to discuss a bit more on these multiplicity one. So this is, I think, in many ways, one of the most important things which happen for these branching laws. That these branching laws have multiplicity one property. Okay, so as I said, it needs to be interpreted properly. And okay, so definition, multiplicity on restriction. So suppose pi is any representation, is a representation of a group G. H is a subgroup of G, and pi prime, let's say, an irreducible representation of H. So given this pair pi comma pi prime, I want to define a multiplicity m pi pi prime to be dimension of the Helm space from pi to pi prime, and these are Helms which are H invariant. So this is the usual formalism of the restriction problem, in which we consider the representations of the subgroup as appearing in pi. But when I say appearing in pi, they appear as a quotient. I mean, one may think of the appearing in pi as a submodule or as a subquotient or as a quotient, but somehow this is what is taken as the definition in the subject. We look at the multiplicity of pi prime as a quotient. And the multiplicity one theorem, so multiplicity one theorems are assertions that m pi pi prime is less than equal to 1 for all pi irreducible of G and pi prime irreducible of H. So, I mean, for thinking about multiplicity one advantage is that you don't need to get into explicit understanding of representations. It is going to be true for all. So parameterization is of no relevance. It somehow sits independent of parameterization because you want to do something for all representations. And there is, so somehow there is this famous theorem due to Eisenberg, Gurevich, Wallace, and Schiffman, which says that for the pairs, the pair of groups G comma H, which consists of either GLN plus 1 comma GLN or SON plus 1 comma SON or UN plus 1 comma UN. Multiplicity 1 holds multiplicity 1 holds for irreducible representations for pi comma pi prime irreducible for G. So these theorems were proved for P-adic groups, and they were then there were theorems also for real groups. Theorem due to this I forget, but same theorem for real groups. Okay, so multiplicity pi is a representation of G of the bigger group, and pi prime is a representation of H. We are looking at the multiplicity in terms of the Helm spaces appearing as a quotient. That's my definition, and as I said, the definition could have been in many other ways, as sum of Jordan-Holder series or as a submodule, etc. But this is the definition which is taken in the subject, and this is good because I think as later development suggest the representations of G when you restrict to H usually has no submodules. No irreducible submodules. And on the other hand, if you look at in terms of Jordan-Holder factors, then it appears with infinite multiplicity. So this is the only reasonable one. Okay, so I think in next few minutes, I want to give you a general framework in which these theorems are considered. And I think it goes under the name of Gelfand's trick. So multiplicity one theorems are proved using a method invented by Gelfand. Called Gelfand's trick. Gelfand's trick. And was later adopted for P-adic groups by Gelfand and Kazdan. There are analogous methods for real groups. You know, for certain matters, real groups are slightly different. Eventually, one expects that the real groups are they have similar analysis at the end, but they have slightly different features. So maybe I make a definition. So for some of these, for next few minutes, I will deal mostly with finite groups to give you an idea of what's going on. And I may draw on examples from non-finite groups, but so G comma H, pair of finite groups. Pair meaning H is a subgroup of G, is called a Gelfand pair. Pair if multiplicity less than equal to 1. Okay, so for the Gelfand pair holds for the trivial representation of H. Trivial representation of H, i.e. Harm I comma 1 with respect to H, this dimension is less than or equal to 1 for all pi irreducible. So it is only about the trivial representation of the subgroup that one is making this assertion, and this is called Gelfand pair. And this one, G comma H, is called a strong Gelfand pair. Strong Gelfand pair. If either holds A is that G cross H comma diagonal H is a Gelfand pair. Or B, this home condition which I said, all pi 1, pi 2. So, in just the Gelfand pair, it is the trivial representation of H which appears with multiplicity less than or equal to 1. And in strong Gelfand pair, all representations of H appear with multiplicity less than or equal to 1. And since any representation of G cross H is pi 1 tensor pi 2, these two are equivalent. So if one understands Gelfand pair, then a strong Gelfand pair is a special case of Gelfand pair for this other pair. So this is just the multiplicity 1 property that we want to understand. And the Gelfand's trick will come soon. So there is the Frobenius reciprocity, which is kind of one of the most basic statements in group representations. It says that Hom pi trivial, pi restricted to H is same as Hom G of pi to induction from H to G. So this is what is called the Frobenius reciprocity, and Gelfand pair is one for which this Hom dimension is less than or equal to 1. And therefore, by the reciprocity, it just means that in this representation, everything appears with multiplicity less than or equal to 1. And therefore, G comma H is a Gelfand pair. Gelfand pair, if and only if endomorphism algebra of induction from H to G of 1 is commutative. Because, multiplicity 1, if you decompose induction from H to G as summation Ni pi I, then the endomorphism algebra is matrix algebras of size Ni's. So this is commutative if and only if Ni's are 1, less than or equal to 1. So this algebra has a very distinguished place in the subject that we belong. This is often called a Hecke algebra. So endomorphisms from H to G of 1 can be identified to functions on G which are bi-invariant under H. Bi-invariant under H. So these are functions on this space. And we are looking at functions on this space. And this space sits inside functions on G, which is the group algebra. And this is a subalgebra under that group algebra operation, which is called the convolution. Algebra is an algebra of functions on G closed under convolutions. Yeah? Sorry? At the moment, I'm dealing with finite groups. You know, in a certain sense, the thing is that once you understand what is the basic argument, one can then generalize. Usually, generalization is not the difficult part. Okay. So still we have not come to, okay, so this is the Hecke algebra. It is a subalgebra of functions on G closed under convolution. And we have not come to Gelfand's trick. And indeed, it is somehow ultimate simplicity. It decides when an algebra is commutative. If P is an anti-automorphism on G, i.e. P of AB equals phi B times phi A, then on an algebra A, yeah, such that P in fact equals identity, then A is commutative. So, of course, it's a pleasure to give you this proof. P of AB is equal to P of B times phi of A, which is phi identity. So this is BA and this is AB. So this is Gelfand's trick. And then it is up to us to use it. So I think a best example, I am not sure that is the original example Gelfand used it for, is the following. So an example. Such that, or with phi equals 1. Yeah, I mean, it's good to see this example. So the example indeed will involve a bit of a non-compact group, but not in a very serious way. And so the group will be GLN QP, and H will be GLN GP. And this anti-automorphism and this Hecke algebra is the usual Hecke algebra that I'm sure everyone here knows about. GL and GP. This is the usual Hecke algebra which appears in number theory. And we will apply Gelfand's trick to the anti-automorphism PG equals transpose G. So everyone, of course, knows that this is an anti-automorphism. And all that I need to say is that on functions here, it is identity. So for this, we invoke what is called Cartan decomposition. Cartan decomposition, which says that GLN QP is GLN GP times the diagonal matrices A times GLN GP. And therefore, on the algebra of functions on bi-invariant functions, they can be treated as functions on A, and on A goes to A transpose is identity. So phi is identity on the Hecke algebra, and therefore H is commutative. So as P equals 1 on A, P acts by 1 on this Hecke algebra. And this implies proving its commutativity. So I think this is a common trick which is used to prove all theorems about multiplicity 1. It also is the common theorem to prove any Hecke algebra of interest, which turns out to be commutative, is commutative. This involution that is here exists in all generality and what is called the Chevalley involution on a reductive group. Okay, so yeah, so this is a bit of Gelfand pairs and strong Gelfand pairs. And all is good? Yeah. As I said, either you deal with trivial or do you deal with all. Strong Gelfand pair has multiplicity 1 for all. Gelfand pair has multiplicity 1 for only the trivial representation. So just to come back to this example, it is what is called the spherical vector is unique up to scaling. But other representations, they appear with multiplicities, high multiplicities. So in this particular case, it is not a strong Gelfand pair, not even for SL2. I mean, indeed, there are many examples of Gelfand pairs, but there are very few examples of strong Gelfand pair. And I believe one of the virtues of GGP is that it captures all examples which are strong Gelfand pairs. There are many examples of Gelfand pairs, but strong Gelfand pair for reductive groups, it is a theorem that only GLN and SON are strong Gelfand pairs. GLN, GLN minus 1, or SON, SON minus 1. These are the only strong Gelfand pairs. But there are many examples of Gelfand pairs. And indeed, they also are well considered in the subject. But if we are dealing with all representations, I guess the examples considered by GGP are essentially the only one. Meaning, when you restrict from G to H, every representation of H appears with multiplicity less than or equal to 1. Okay, so yeah. So I want to make a general comment. You know, we are looking at algebra of double cosets. Algebra of double cosets, G mod H on the two sides. I mean, very familiar to number theorists, algebra of double cosets. And we want to say that functions on G which are bi-invariant are yeah. So Gelfand's trick for G comma H and an anti-automorphism phi E works. So, you know, that anti-automorphism phi is an anti-automorphism on the group. And in some sense, the most visible anti-automorphism on a group is G goes to G inverse, or composed by an automorphism. And for GLN, there is G goes to G transpose. So in a certain sense, coming up with phi is not a big deal. But what is somewhat non-obvious in examples is to understand that it acts by identity. That is what is non-obvious. We use the Cartan decomposition to prove that it acts by identity. So works if one knows that he reserves all double cosets of cosets of G. This is a group theoretic property that you need to prove, that you are given an explicit anti-automorphism and then you want to prove that something happens. And in the strong Gelfand pair, or strong Gelfand pair, one needs to prove that PG and G are conjugate, perhaps PG and G inverse, or conjugate, no. Yeah, or conjugate under H. Meaning phi preserves all the double cosets, whereas in this case, there is a slightly different interpretation if you take G to be G cross H and H to be diagonal H. And okay. So before I say that, I forgot my good friends. So these are people Ting Bo Ju and Binyong Sun. All right. So yeah. I am in these lectures dealing only with complex representations. The groups are finite groups, as I said. Sometimes I am dealing with other groups, but for that one, there is no extra work needed. For some other things, some extra work is needed. Okay. So, these are one knows. So the Gelfand trick is that there is an anti-automorphism which preserves all the double cosets. Another way to interpret this condition is that on algebra of functions, which are H by invariant, phi operates trivially. So this condition is equivalent to say that phi acts trivially on algebra on functions which are H by invariant. And this also can be interpreted. So this is roughly how the method works in P-adic groups also. But instead of looking at functions, one looks at distributions on the group G. So just a quick word, a distribution on a P-adic group is a linear form on the space of locally constant, compactly supported functions. Okay, so distribution on GQP. So as I said, there is this notion of the Schwartz space of GQP. This is equal to algebra of locally compact, locally constant, compactly supported functions. Functions on G. And a distribution on G is just a linear form. On GQP is a linear form from L from the Schwartz space of GQP. And the theorem of Gelfand and Kazdan is roughly, I think it is just a little mild caveat there, but I will not worry to bother you with that theorem. This is the theorem due to Gelfand and Kazdan. Multiplicity G comma H is a Gelfand pair for p-adic groups. Pair for p-adic groups. If on a space of H bi-invariant distributions on G, phi operates trivially. If on the space is of H bi-invariant distributions on GQP, P acts by 1. So if we were dealing with finite groups, then whatever I said earlier and this statement are the same. But for p-adic groups, this is what is proven. And with so, when I say this is a Gelfand pair, this is an assumption that phi acts by 1, and the conclusion is that multiplicity 1 holds. Sorry, Rajan. Anti-automorphism. Okay, so I want to tell you what is done in this theorem of Eisenberg, Gurevich, Rallis, and Schiffman to prove these are Gelfand pairs. So by that second remark, what one needs to prove, so proof of AGRS. Meaning, I want to say how one begins the proof. So again, the involution will be G goes to G transpose. G goes to transpose G is the involution phi. And what one needs to prove is that this involution acts trivially on all distributions on GLN plus 1, which are invariant under conjugacy by GLN. So theorem, any distribution on GLN plus 1 QP, which is conjugacy invariant by GLN QP, is invariant under conjugacy by GLN QP sitting inside GLN plus 1 QP, is invariant under phi. So, this statement you will all recognize is a form of a well-known theorem in linear algebra, which says that for a matrix G, G and G transpose are conjugate. But here it says a little more. One is roughly trying to say that inside GLN plus 1, not only a G and G transpose conjugate, but the conjugation can be effected by an element in GLN. It is a slight refinement. And one of the things which works for P-adic group, because there is some topology involved, is that this statement is not true on the nodes. Not every matrix of GLN plus 1 is conjugate to its transpose by GLN. But enough matrices are conjugate, and therefore, as a statement on distributions, it holds. So the proof, it builds on the observation that G and transpose G are conjugate inside a GLN are conjugate in GLN plus 1 QP. But now we want to see this conjugation happen inside via an element of happen via an element of GLN QP. So, you know, of course, one might say that in many mathematical problems, before one converges to a proof, one wants to check whether this looks reasonable or not. And one way to check reasonability is via some kind of a dimension count. And I might do that to see how this may be a plausible theorem. So we want to conjugate G transpose X, G, X inverse. This is what we want to achieve. And this we already know is true for GLN plus 1. So here X belongs to GLN plus 1. But you know, what is the ambiguity involved in this equation? You know, if we multiply X by a centralizer of G, it doesn't matter. On the other hand, if you multiply X by a centralizer of G transpose, it doesn't matter. So therefore, the ambiguity involved in X in GLN plus 1 QP is a double coset space. GLN plus 1 QP modulo centralizer of G and modulo centralizer of transpose G. And what we want to say is that this is GLN QP. If we can say that, then we are good. But I think what we are going to say is that this is true for most G's. And the way it works is that, you know, we can take G to be what one may call regular semi-simple element. Then the centralizer of G is a maximal torus, not necessarily split, a maximal torus. And that also is a maximal torus. And generically, one may expect that these tori have nothing to do with each other. And now let's do the dimension count. And you know, this center, centralizer of G and this centralizer of G certainly have the center of GLN plus 1 in common. So we have to subtract 1. Inclusion-exclusion principle. So the dimension involved here is n plus 1 square minus 2 times n plus 1 plus 1. And I hope it is n square. So one will say that it looks plausible. And maybe this can be made. But I think I have not seen a very precise statement when this happens. I am sure there is a precise theorem which says that this is true if and only if. So this is, I am proposing for young students as an unsolved problem. It's a precise question. Try to classify all matrices G in GLN plus 1E which have this property. All right, so I leave it at that. I mean, the theorem of AGRS is from 2010. And Rallis had told me for long years, this was expected to be true. And he had told me that it is among the most difficult things he ever tried proving. So there are some technical details. Okay. So in the remaining few minutes, I want to I want to begin another topic. Or maybe I can pause, and if there are any questions, I can address them. No, I am not saying that. I am giving this as an open question. Not true. I thought I had one, but we will come back to that. Okay, so the next topic, which I wanted to, but I think there is not too much time, but I will anyway begin. So, you know, I have been emphasizing in the lecture today that multiplicity 1 theorems are crucial. And I think it is something which cannot be overemphasized, how important role they play in any kind of representation theory. So so we are dealing with some local problems. We already dealt with uniqueness of the spherical vector. That the spherical vector is unique up to scaling. The k fixed vector is called the spherical vector, and that is unique up to scaling. There is another uniqueness theorem called the uniqueness of the Whittaker model. And that is also, so perhaps the Gelfand's trick was invented to prove the uniqueness of the Whittaker model. And so that is also unique. The other thing which is unique is, so this is what I was going to talk about. So people study space of functions on GA which are invariant under GQ. And what we will be doing is looking at submodules of this. And it is a very classical theorem for GLN that every submodule appears with multiplicity 1. That goes with a combination of uniqueness of the Whittaker model and so on. And that assertion is also known to be true for all classical groups, which is what the GGP conjectures are about. So for classical groups to say that something sits there, it sits uniquely. You know, if it was appearing with multiplicity 2, then one cannot say pi sits there. You know, because it is pi direct sum pi, and it can sit in many ways. So multiplicity 1 allows one to identify, to confuse between an abstract automorphic form automorphic representation and a submodule of L2. So perhaps there is not too much time, but I will just define what is called period integral. And so if you are given, let's say, f, the function in pi, which sits inside L2 of GQ mod GA, then one of the things one can do is to integrate this function. F goes to integral of f dh on HA mod HQ. And this is an HA invariant linear form by the very definition of Haruzo. So this is an HA invariant linear form on pi. And this HA invariant linear form on pi is called the period integral. So, you know, if a representation has an HA invariant form, and this representation pi itself is what is called a restricted tensor product of representations pi v of GQV, then each of these pi v's will have an HV invariant linear form. Then if integral of f is not identically 0, this implies that form of pi v comma c over hv, this is not 0 for all v. So these are called local conditions for non-vanishing of the period integral. And one of the aspects of GGP is to ask the converse. So this is what is called local global principle. A global object is there or not there, has implications locally, and whether those local implications imply the global existence. So GGP addresses whether local conditions ensure the non-vanishing of the global period integral. And I mean, of course, I think it needs to be emphasized time and again that all of GGP is directly inspired by earlier works due to Walsh-Purgey. I mean, in a certain sense, most of the formalism is already in Walsh-Purgey. So I guess what GGP should be credited for is to identify the pairs for which the Walsh-Purgey works. Okay. And the theorem eventually, theorem, conjecture, and perhaps a theorem in many cases. Conjecture, period integral, not identically zero if and only if local conditions A and B and L half of, let's just say, pi1 tensor, pi2 is not zero. So I think most of my lectures are about part A, which is also quite demanding. I mean, to define L functions, etc., of course, is perhaps easier to do. So we will continue. All right, thank you.
Any question? Well.
No, Walsh-Purgey wrote very, what is it called, earth-breaking papers in the early 80s on what is called the toric period. So the GGP problem, so the restriction problem from GL2 to a torus. So the question is, if you take a modular form on GL2, treat it as a function on GL2A, and you integrate that modular form against a Grossen character on the torus. What are the period integral, and if one can say when it is zero or non-zero. So he gave a template to make assertions of this kind. And as I said, one of the things for which GGP could be credited is to find a framework in which Walsh-Purgey works. I mean, Walsh-Purgey himself was trying to generalize a famous work of Hecke that if you do it for split torus, then this is the usual L function. Hecke proved what is called the Mellin transform, f of it, t to the power s, dt by t is equal to ls pi. And one of the details that I wish to bring to your attention is that, for Hecke, it might be a very specific new form, etc. And it is equality on the nose. And to have such equality on the nose, you have to really be very precise about what f is and so on. And typically, these multiplicity one theorems only tell you that something is unique up to scaling. But number theorists are not interested in unique up to scaling. They want to get a number. Pi is equal to pi. And not that pi is an unknown multiple of pi. I think it is almost as good as no theorem. So it needs a certain conceptual framework in which you can bring these multiplicity one theorems to make a precise statement even when things are only unique up to scaling. I mean, roughly you want to say that the integral of f is L value. But there is nothing called F. Nothing is unique on the nose. Only in theory of holomorphic modular form, you can make F unique by saying that A naught is equal to 1 or A1 is equal to 1. A1 is equal to 1, A naught is 0. So only in the theory of elliptic modular forms, there is a nice normalization. And if you want to make a statement that L value is equal to, no, the period integral is equal to L value, I mean, what F are we talking about? All right, so I think some of these matters I will address. Anyway, it can be only some very broad stroke exposition.
So let's thank speaker again.